Okay, how many questions we got? This is period 8, so there must be a lot. And we got to learn about partial fractions today. Okay, now remember, tomorrow's quiz is on rational 1 and 2. Okay, there's 3 graphs and 2 regular problems. What the heck are you doing? Okay. Oh, we got 1 graph. Ah, boo! 1D. I thought we had the graphs down. Or is it because it has an absolute value on it?
Yeah.
No! Okay, what did we learn last chapter? When you see absolute value, A, pretend it's not there. B, skip to the next problem. C, write a piecewise function. Yes, you write a piecewise function, that's automatic. So, x is greater than or equal to 0 and x is less than 0. Remember, how does absolute value work? It's either equal to itself or the opposite of itself, right? So when x is greater than 0, it's equal to itself. So you get x plus 1 over x minus 1. If x is less than 0, what am I doing? Less than 0, then it's equal to the opposite of itself. So negative x plus 1 over x minus 1. Oh! But this simplifies to negative 1. Please simplify, because I remember on the test, the last test, you guys don't simplify, and of course then you don't recognize on the graph. Okay, now, this, everybody knows how to graph y equal negative 1, right? Just a horizontal line, which is this one. How do you graph this one? This one's easy. X-intercept, negative 1. Y-intercept, I'm just going to do this fast. Vertical asymptote, x equal 1. Horizontal asymptote, y equal 1. Right? So the graph looks like this. But we are only graphing it when x is greater than or equal to 0. So that means to the right of the y-axis. So from here to the right, and then okay, now when x is less than 0, then you graph the line y equal negative 1, which is simply a horizontal line like that. And that's what the graph looks like. You make a piecewise function. Well, what did you guys do? I see an absolute value. I don't know what to do. Is that it? You were trained. I'm trying to train you for calculus. In calculus, you got to know how to handle absolute value. Make a piecewise function. That's how you handle it. Okay, number 2 you can do, but not number 3. That's so strange. But this is period 8.
I was going to put them both on, but then you'd be not saying that.
I'm mad anyway. You mean you cannot graph this? Tomorrow's graphs are way harder than this.
No, I just don't understand the limit part.
Oh, good thing you came in for help then. Didn't we talk about this last time?
Yes. No, we talked about graphing last time.
Yeah, and wait, did we or did we not? Everybody said yes. We talked about limit. Maybe you got to start paying attention.
No, I watched the video too and I still got it.
So again, good thing you came in for help this morning. Okay, did you draw the graph? X-intercept, negative half. Y-intercept, 1. Vertical asymptote, x equal 1. Horizontal asymptote, y equals 0. So the graph looks like this. And then, okay, now answer the questions. A, what is the limit as x approaches negative infinity? In other words, as the graph is going out to the left, the y coordinates are getting closer to what number? Look, the graph is going out to the left. The y coordinates are getting closer to what number? Y. Because the asymptote is y equals 0. Because look, the y coordinate here is like negative 0.5, negative 0.4, negative 0.3, negative 0.2, negative 0.1, negative 0.01, negative 0.00001. Isn't it getting closer to 0? Yes, that's what limit is. What is the y coordinate doing as x approaches the number? So part D, what is the limit as x approaches, wait, Oh, 1 from the left. Okay, here's x equal 1 right here. Here's x equal 1. Coming from the left, look. What's happening to the y coordinates? Yeah, infinity. C. What is the limit as x approaches 1 from the right? Okay, here's x equal 1. Coming from the right. What's happening to the y coordinates? Infinity. And then D. Isn't that what we explained? We talked about this last week. What's the limit as x approaches infinity? As the graph is going out to the right, the y coordinates are getting closer to what number? Y. Because that's the horizontal asymptote. This is how we describe asymptotic behavior, using the limit thing. Did you ask permission to eat? Too late. No. If you ask before, the answer is yes. If you ask late, the answer is no. It's like killing me. Number 4. You guys can do 4 but not 5? That's so strange. But then again, this is period 8. 5. Write a rational function so that its asymptotes are x equal 2 and y equal x plus 1, and it has a removable discontinuity at negative 1, 1. Okay, so the slant asymptote, it has a slant asymptote. Now remember, so again, this is like going backwards. How do you find the slant asymptote? What do you have to do? You do division, well, not necessarily synthetic division, because sometimes you got to do long division. You do division, and when you divide, what do you get? Don't you get the quotient plus the remainder over the divisor? That's what you get when you divide, right? Which one tells you what the slant asymptote is?
The quotient.
Okay, so if the slant asymptote is y equal x plus 1, doesn't that mean x plus 1 is there? Because don't we just ignore the remainder part for the slant asymptote? Okay, so we're just going backwards. It's like the same thing. And then, if you want a vertical asymptote at x equal 2, doesn't that mean you need x minus 2 in the denominator? So shouldn't the divisor be x minus 2? The only thing we don't know is, what is the remainder? What is the remainder? Well, it says, well, forget the removable discontinuity for now. The graph has to pass through the point negative 1, 1. So what do you think I'm going to do with that? Yeah, you plug it in. You plug in negative 1 for x and 1 for y. That's how you figure out what the remainder is. So 1 equals negative 1 plus 1 is 0, plus the remainder over negative 1 minus 2 is negative 3. Can I figure out what r is? Yeah, r equals negative 3. So that means the equation was y equal x plus 1 plus negative 3 over x minus 2. And then of course, we simplified, we make a least common denominator, which is x minus 2. So what goes on the top? This is like over 1 and over 1. X squared minus 2x plus x minus 2 minus 3, which simplifies to x squared minus x minus 5 over x minus 2. Yeah, but Mr. Park, that's not the answer. That's because this is not just a point on the graph, it's a removable discontinuity. That means there's like a puka there. So, how do you get removable discontinuities in the graph? Yeah, you gotta cancel. So if you want a removable discontinuity when x is negative 1, what is the factor that has to be canceled?
X plus 1.
Yeah, so what you have to do now is multiply top and bottom by x plus 1. So you can cancel it out, and that's how you get the puka there. And then of course, I will let you multiply that out.
That'd be the only correct answer.
Yes, there's only one correct answer. Wait, what are you thinking?
I did it by. Shoot, I erased on my book, but.
Okay, stop listening already. We're moving on. Number 6. Oh, I told you about this. Where does a graph cross its horizontal or slant asymptote? This problem is on the test. You don't even have to ask.
Not on the outside.
Well, you make
What?
it equal to the.
I don't even know what you're talking about. Okay, here is the graph. What is its horizontal asymptote? Well, if the degree of the top and the bottom are the same, you look at the coefficients. So what is the horizontal asymptote?
2.
No,
Y
y
equals
equal 2. Okay, so how do I figure out where these two graphs intersect?
Substitution.
Yeah, substitution. You just substitute 2 for y and you solve it. This is actually super easy. Cross multiply. So cross multiply. So 2x squared minus 8 is equal to 2x squared plus 3x plus 1. Oh, the 2x squareds cancel out! And you get 3x is equal to negative 9. Therefore, x equals negative 3. So we know that these two graphs will intersect when x is negative 3. How do I figure out the y coordinate? Plug it into this one or that one. Doesn't matter. I think I prefer that one. 2. Well, duh, if it's going to cross at the horizontal asymptote, doesn't the y coordinate have to be 2? Okay, if you don't trust me, plug the negative 3 in there. I bet you get 2. Although some of you might not get 2 because your arithmetic skills are atrocious. So can you think ahead? What's going to be on the test now? Where does the graph cross its slant asymptote? What would you do? Yeah, so what you do is you find the slant asymptote and you write that down and then you substitution and you solve it, right? It's the same thing, except different. Okay, number 7. Oh, you guys got 7, 8, and 9. Very good. Oh, so now number 8, we got it then. See, remember this odd even thing? F is even. Oh, therefore A gotta be 0. You guys are good at that now, after last chapter. Okay, so I told you what the quiz is. The quiz is gonna have 3 graphs. One of them will have a slant asymptote, the other 2 on horizontal asymptote, and then 2 regular problems. You can probably guess what they are. Yeah? Like from 2 to 9. I'm not gonna tell you. You want me to just tell you what they are?
Yeah.
That's shameless. Oh, who's the part that you tell me the exact problems? That's sad.
What's the answer to why?
Okay, now, normally in the past, Algebra 2 honors, they would like at least touch on partial fractions. Like Mr. Mubash would do like a bonus quiz or something. Did you guys even have bonus quizzes last year? What's a bonus quiz? But now, so you guys absolutely have no idea what a partial fraction is then.
You just break up and calculate.
Yeah. Where did you learn that? 5th grade. Now, why is that important? Why is it important? Because your dad taught it.
To get to where everything came from.
No, that's because, well, yeah, I guess that too, but then in calculus, that's an important skill because if you don't break it down into its partial fractions, then you can't even do the problem. Okay, so let's go back to Algebra 1, okay? Do you guys remember how to add fractions? You sure? Like if you have 3 over x plus 2 plus 5 over x plus 3. How do you add fractions together? What do? You make a least common denominator. So the least common denominator is this. What goes on the top? 3 times
X
x plus 3 plus 5 times x plus 2. Simplify the top, so you get 3x plus 9 plus 5x plus 10. This is just algebra 2. I mean, what am I talking about? 1. So your final answer is 8x plus 19 all over x plus 2 times x plus 3, correct? Yes. Okay, that's algebra 1. Okay, now we go backwards. I give you this, and you have to decompose it into its partial fractions. That's what we call it, decomposing it into its partial fractions. I give you this, decompose it to that. Like what fractions added together will give you this as the answer. Believe me, if you can't do this in calculus, you can't do calculus. Calculus is easy. The pre-calculus part is the hard part. So, I will show you how to go backwards. But you have to have common sense, which might be a problem. Okay, now think. What fractions do I have to add together so that I get this as my answer? Doesn't it have to be something over x plus 2 plus something over x plus 3? Because that's how you're going to get this as the LCD, right? So all you gotta do is figure out what the A and B are. Now, one way to do it is, every year students wanna guess and check, okay? And if I make the answer come out nice like that, then you probably can guess and check. But what happens what if instead of 3 and 5, it's like negative 2/3 and positive 7/3? Who's gonna guess that? So you need a mechanical way of figuring out what it is. Okay, so I'm gonna show you that way. Okay, but first, does everybody understand this? What fractions added together will give you this? You sure? Okay, this is an easy one. Okay, when we get the harder ones, then you're gonna go, what? Okay, so watch what I'm gonna do. Clear the fractions. Multiply both sides by the LCD. You'd be surprised every year how this step trips up people. I don't know why, but it does. If I multiply both sides by the LCD, you get this, right? Now, once you get to this step, there's two methods of doing it. There's two methods, and I'm not gonna tell you which one to use. You just figure out whatever works for you. The first method is called equating the coefficients. Okay, that's the first method. Now, equating, okay, I'm just gonna leave this up here because we know that's the answer, and we've gotta get there. Okay, now what does equating the coefficients mean? Well, what if you have this? What if somebody says ax plus b is equal to 4x plus 1? What can you conclude? A equals 4 and b equals 1. That's called equating the coefficients. The coefficient of x on the left got to equal to the coefficient of x on the right. The constant on the left got to equal to the constant on the right. Doesn't that just make sense? This is called equating the coefficients. So that's what we're going to do here. So 8x plus 19 is equal to, then you multiply all this out. ax plus 3a plus bx plus 2b. And then you group it. Here are the x terms. If I factor out the x, what's the coefficient going to be? A plus b. And here are the constant terms, so that's going to be 3a plus 2b. So by using common sense, a plus b gotta equal 8. The coefficient of x on the right gotta equal to the coefficient of x on the left. And then the constant on the right, which is 3a plus 2b, gotta equal to the constant on the left, which is, this is called equating the coefficients. And then you have two equations, two variables, and you solve it.
Whoa.
Using algebra 1. Like if you were to solve this, what do you want to do? You want to do substitution or addition, subtraction?
Subtraction.
Yeah, if I were me, I would multiply the first equation by 2, so you get 2a plus 2b equals 16, and then I would subtract these two, so you get a equals 3. Once you figure that out, plug it back here, b equals 5, and there you go, see? 3 and 5. So that means a is 3 and b is 5. Oh, Mr. Park, it's harder to go backwards. Yeah, that's why you learn it in Algebra 2 and pre-calculus, because Algebra 1, they couldn't do this. Okay, that's equating the coefficients, okay, but there is another way. And this way is going to seem to be way faster, but in some situations, it's not faster. This is called the Heaviside method. The Heaviside method, named after the engineer and mathematician Oliver Heaviside. Oh, you knew. How come he knows and you guys don't know? And he's 1 year younger.
His dad tells him everything.
My dad made me take a math history class.
Maybe every guy should make.
He said no.
No, but I want to take piano lessons. Okay, anyway, watch what I'm going to do. This is. So no, sometimes you got to weigh that. Do I want to make my child take piano lessons, violin lessons, or math lessons?
Well, I feel that the piano and the violin, so that's why he made me take it.
Okay, whatever. Or should I play sports? Why can't you do all? I mean, elementary school hardly got any homework anyway, right? There you go, that's the problem. Okay, the Heaviside method, now watch. This guy was very clever. Oliver Heaviside said, ooh, why don't I just plug in numbers for x? So he said, ooh, you have this equation here, I'm gonna plug in negative, now you can plug in any numbers you want, but if you plug in good numbers, it comes out really nice. Why did he pick -2 to plug in for x?
Because it makes.
Why didn't he plug in like 0 or 1? Why did he pick -2? Yeah,
Yeah,
because it makes this thing 0. So watch, plug in -2 for x, plus 19. 3 is equal to, plug in -2 there, you get a plus 0. Oh, a is 3, finished. We just figured out what a is. Some of you are not seeing it. Okay, now let's plug in another number for x. What do you think? -3, because it makes that term 0. So if I plug in -3, you get -24 plus 19.
5.
Is -5 is equal to 0 plus -b. Oh, so b is 5. Finished. So that means a is 3 and b is 5, which is of course the problem that we started with at the beginning. And that's how you decompose it into partial fractions. Now, like I said, this way is way faster if you have linear factors. See how x is to the first power? But you're going to learn in the homework, like not all the time do you have linear factors. What happens when you have quadratic or cubic factors? What do? And sometimes equating the coefficient is actually faster, or you use a hybrid of the two. No, if you want to, it doesn't matter. You could just use this the whole time, you could use that the whole time, but it just might take a little bit more work. So that's what you have to discover when you actually do the homework, is what's the best way to do it. Okay, so I showed you the way. So the key to doing all of this is to set up the problem correctly. Because if you don't set up the problem correctly right here, then that's a fatal error. That's -8. So you can be doing like 10 minutes of work, it's not going to count as -8. You have to set up the problem correctly. Now, if you look in your notes, I gave you lots of examples, but you guys don't even look at the notes. So, I guess I will have to do it for you. Okay, what if you had something like this? Now, let me mention something. Before you can even set up the problem, you got to make sure it's a proper fraction. You guys know what a proper fraction is? The degree of the top is smaller than the bottom. So if the degree of the top is not smaller than the bottom, like if you look at the last two problems of tonight's homework, then before you even start the problem, you have to divide first. You know what I'm talking about? Like what if you had this? 8x cubed plus 2x squared plus 5x plus 3 all over x squared minus 4. Why don't I just factor it already? X plus 2 times x minus 2. Okay? Look, the degree of the top is 3, the degree of the bottom is 2. If the degree of the top is not smaller than the bottom, you cannot even start partial fractions already. So you have to divide before you even start the problem. You guys understand? Because this means divide. Okay, hopefully we have time at the end. Okay, so let's just practice setting up the problem, because like I said, if you don't set up the problem correctly, it's a fatal error. Okay, let's start with an easy one. What if you had 2x plus 1 over x times x plus 2 times x minus 3? Okay, now think. What fractions, when added together, will give you this as the least common denominator? Something over x plus something over x plus 2 plus something over x plus 3, right? That's easy. Okay, that's easy. Okay, now let's kick it up a notch. What happens when, notice that all of these are linear factors, they're all to the first power. First power, first power, first power, linear. Okay, but what happens when you have a repeated linear factor like this? What if you had, I don't know, 3x squared plus 2x plus 1, the numerator part really doesn't matter, all over x cubed times x plus 2 squared.
You have to do x squared.
There you go. Okay, now this is the mistake students make. What fractions, when added together, will give you this as the least common denominator? This is what students normally do. They go, oh, easy, something over x cubed plus something over x plus 2 squared. Well, I would agree, if you add these two fractions together, that's the least common denominator, but that's not the most general case. So if you did this on the test, minus 8 already, because it's all wrong. This is what it should be. Something over x plus something over x squared plus something over x cubed plus something over x plus 2 plus something over x plus 2 squared. What? Well, let me ask you this. If I add these 5 fractions together, what's the least common denominator? That. And that's why. So when you have a linear factor to a power, you have to have that power plus all the ones that come before it, all the way down to 1. So like if this was 5th power, you would have to have x to the 5th, x to the 4th, x to the 3, x to the 2, x to the 1. You guys get it? Okay, so that's linear factors. Okay, now what happens when you have quadratic factors? And then repeated quadratic factors. Okay, so what if you had something like this? 3x plus 2 all over x plus 1 times x squared plus 1. So the first thing you got to do is you got to factor everything. See, this one you can't factor anymore, right? See, this is a linear factor, x to the first power. This is called a quadratic factor, x to the second. Okay, so what fractions when added together will give you this? Now, here's the mistake students always make. They go, oh, easy, Mr. Park. Something over x plus 1 plus something over x squared plus 1. Now, I agree that this, if you add these two fractions together, that's the least common denominator, but you don't have the most general case here. This is what it should be. It should be bx plus c over x squared plus 1. What? That's because partial fractions only works on proper fractions. The degree of the top got to be smaller than the bottom. So what's the degree of the bottom here? 1. What's smaller than 1? 0. What's the degree of the denominator here? 2. What's smaller than 2? 1 and 0. Not just 0. 1 and 0.
Wait, so how come the top one just has to be?
That's because these are all linear factors. These are all first power. What's smaller than degree 1? 0, which is a constant, right? Degree 0 means constant. So when you have linear factors, you're just going to have just a single letter on the top. But when you have quadratic factor, then you got to have degree 1 on the top, bx plus c. And then what? Okay, let's extend. I'm not going to give you cubic factors, but if you did have a cubic, can you think of a cubic that can't be factored, like x cubed plus 5? What has to go on the top? What's smaller than degree 3? 2, 1, and 0. So you would have to have ax squared plus bx plus c on the top. I'm not going to give you that, but that's what would happen. You have to see that so that you can understand it. Okay, now, what happens when you have repeated quadratic factors and linear factors? So, let's do the same thing. Go 3x plus 2, but on the bottom, you got x plus 1 cubed, and then you got x squared plus 1 squared. Same thing over here, like when you have a repeated thing. So how do you set this up? A over x plus 1
plus b over x plus 1
b over x plus 1 squared plus.
c over x plus 1 cubed.
Is your father an engineer or something? Mathematician? Where does he work then?
Oh, they're just tutors.
Oh, okay. Oh, because engineers, you got to do this stuff too. And then what about this one? Ax, oh no, we're on D now. Dx plus e over x squared plus 1 plus fx plus g over x squared plus 1 squared. That's how you set up the problem. That's why I gave you lots of examples if you look at the notes. In fact, this is probably these examples right here. So you guys understand, when you have a linear factor, then you just put ABC on the top, just constants. But when you have a quadratic factor, then you gotta have a linear thing on the top. And then if it's raised to a power, then you gotta have that power plus all the ones that come before it. Now, there's no way I would give you this problem on a test, okay? Because you would have to find 7 letters, which would take you a long time, yeah? The most I'm gonna give you is 4 letters to find. You're not gonna have to find more than 4. Okay? Well, I'm just showing you this so that you understand how to set it up. Okay, so do we get it? Now, what happens, okay, somebody read me the last 2 problems. What happens when the degree of the top is not smaller than the bottom? I'll just start it for you.
7 is 2.
Okay, 2x cubed
Minus 4x squared minus x minus 3.
all over.
X squared minus 2x minus 3.
Okay, so the first thing you gotta do is, well, first of all, you notice, is the degree of the top smaller than the bottom? No, so before you even start the problem, you have to divide. And since we're gonna do long division here, so 2x cubed minus 4x squared minus x minus 3. Divide that by x squared minus 2x minus 3. X squared goes into that how many times? 2x, so multiply times the divisor. 2x cubed minus 4x squared minus 6x. Subtract.
8x squared.
What? No, we're subtracting.
Oh.
Negative, sorry, I'm just kidding, 5x.
5x minus 3. So if you divide this by this, what do you get? You get the quotient plus the remainder over the divisor. Now, do you see this remainder part? See how the degree of the top is smaller than the bottom now? Now we can do a partial fractions on that. So now you do this. You go 5x minus 3 over, and then you want to factor the denominator, x minus 3 over x plus 1. Okay, what fractions do I have to add together to get that LCD there? A over x minus 3 plus b over x plus 1. And then you can, probably the Heaviside method is the fastest way to do this. And then once you get the answer here, don't forget to add the 2x to it. So it's going to be 2x plus the answer that you get here. So you got to watch for that now. So probably on the test, because it'll be a shame to get, you do all the work and you get -8 for nothing. So probably on the test, it's going to say like, hint, the degree of the numerator is not smaller than the denominator. You better divide first or something. Do you really need that hint? Otherwise you're going to get -8. Because if you don't divide first, you're going to get an answer, but that answer is not going to be correct. That's why the key to doing partial fractions is setting up the problem. You have to set it up correctly. Okay. This is the last of the lecture. You just got to get good at it now. Okay, so tomorrow we have a quiz. So when is the test going to be then? Friday, yeah? Great. That's Friday. Okay, we are done. Oh, we finished pretty good. 6 minutes left.
Well, what homework is you on? 3 or just?
3.
2? Okay.
Tomorrow you're handing in 1 and 2.
Not 3.
Okay, no, you want to hand in 3 then, before we discuss it. No, you're only... When do I ever quiz you on things we haven't discussed? Never. Unless I could start now this year for the first time.